Welcome back to the channel, and today we're doing the small signal analysis of the common source MOSFET. So as always, we're going to compute the voltage gain, input resistance, overall voltage gain, and the output resistance. And to the right is the equivalent circuit model. And let's hop right into this. So the first thing we want to do in any small signal analysis is always draw the the circuit in the small signal domain. So that means we short circuit the capacitors and deactivate all the DC sources, which in this case is the current source in the source and the VDD. So as always, we always draw the circuit model first and then we add the components. So here's the gate, source, and drain. And I labeled the gate, drain, and source on the circuit figure. And so in the gate, what we notice first is that we see there's a gate resistance RG. We short circuit the capacitor, we have the voltage in terminal, and then we simply have our AC components. And the source attached to the ground. Now for the source, we see that we have a source resistance, RS, and then the current source gets open circuited, so that we just don't even have to worry about that. And the capacitor gets short circuited, so this is just connected to the ground. Now for the drain, we see that we have these two resistances, which once we short circuit the VDD, both will be connected to the ground. So we can simply write this as RL in parallel with RD, V out. Now you should be able to notice this with a bunch of practice that right away they should be in parallel. So now that we have the circuit in the small signal domain, we can start computing the values. So for the voltage gain, I found this was actually the hardest thing to find out of all the transistors. It does take a little while, but I think I found the easiest way to do it. And there's a lot of ways to do this. For example, you could do a bunch of KVLs, but it just end up with too many equations and the algebra would get really difficult. So my favorite way would simply just be to perform KCLs at node A and KCLs at node D. Sorry, we should actually call A node S. So why are we doing KCLs at node S and D? Well, we see that node S and node D are all connected to V out and V in. They're both functions of V in and V out. Now, how do we know that? Because the VGS is controlling the current source. Now, VGS we can simply find an equation for using KVL. Let's do KVL. Let's write that in black. So we know that VGS plus Vs minus Vin equals 0. So we can simply write VGS equals Vin minus Vs. Now you should honestly be able to tell that right away because the gate voltage here is Vin, but just logically it would be a KVL there. And now we can see that we can connect the dots and see that the drain node and the source node, once we perform KCLs, we'll be left with just V out and V in. So let's get started. Let's first do the KCL at node S. So what do we get from that? We see we have GM VGS plus the current in the resistance, RO, which will be V out minus Vs over R out. Now, why is it V out minus Vs? Because Vs is the node voltage across here, and V out is obviously going to be the voltage at the drain node. So that is all equal to Vs over Rs, sorry. So now we have our first equation. Let's perform another KCL at node D. So we can simply see that all of these will be flowing downwards. So we can write 0 is equal to GM VGS plus the current and the resistance R out. So we have V naught minus Vs over R out plus V out over RL in parallel with RD. So immediately what we can notice is we have a voltage Vs, which we don't have anything for Vs. We need to find a function for Vs that we can plug back in to make it only V out and V in. So what we can simply do is we know that GM VGS is going to be equal to GM V in minus GM Vs. So once we plug that into the first equation, we'll call this equation 1. We'll write an arrow pointing into 1. We get GM V in minus GM Vs plus V out minus Vs over R out equals Vs over Rs. So now what we can do from here, we can simply solve for Vs. So Vs 1 over Rs, once we move Vs to the other side, plus 1 over R out plus GM equals V out over R out plus GM V in. Now, simply what we can see is we can divide both sides by whatever is in this bracket, and then we're just left with a function of V out over V out and V in as Vs. Now, I'm not going to go through all the algebra just because the whole point is to teach you guys how to solve the circuit, not how to do algebra. So once we have this, let's label this equation as equation 2. We can plug whatever we get from here, we'll call this equation 3, back into equation 2. And now, so equation 2 will actually look like this. 0 equals GM V in minus GM Vs, which we'll plug into here, plus V naught over R out minus Vs over R out plus V out over RL in parallel with RD. So once we plug the formula for Vs into our equation 2, then we simply see that all we'll be left with is functions of V out and V in. Now, what we can do from there, we can simply just factor out V in and V out, and we'll get an equation on one side only in terms of V in, and an equation on the other side only in terms of V out. So then from there, we can just divide both sides to make it V out over V in, and simply compute the answer from there. So I'm not going to go through that with you guys just because the algebra would be really difficult, and once you have actual numbers, then it becomes a lot easier because you can just plug the numbers in. But so that's kind of the general gist of it. And now let's move on to the input resistance. So for the input resistance, again, we're simply just finding the Thevenin equivalent resistance from the circuit, from the outlook of the V-in terminal. So we're basically saying we're finding the Thevenin equivalent circuit of what I just underlined. So in order to do that, we'll just simply add a 1 amp current source. And this is all connected to this. Now, I really want to state that this stuff here really doesn't matter, whatever's on the other side of the circuit. Why? Because, well, we see that this circuit on the gate is not even connected to the source and the drain. And what we're looking for in R in is V in over I in. So Clearly the input current is just going to be in the gate because it's not connected to the drain and the source. So we're only looking at the gate right now. So we know that I in is equal to 1 amp. So what we can write is V in equals 1 times R, which will be RG. So V in equals RG. So once we plug this back into our original formula, we can simply say that Rin equals Rg divided by 1, which is simply just Rin equals Rg. And now for the overall voltage gain. So we know the Rin value, which is Rg. We can actually replace that with Rg. Now, why does the circuit just look like this, you might ask? Just because we found the Thevenin equivalent resistance for the entire circuit from the outlook of the Vin terminal. So we can actually replace that circuit with just one resistance. And now simply what we can do is GV equals V naught over V sig. But we can manipulate this formula to make it easier for us, actually. We can multiply it by Vin over Vn. Why would we do that? Because that just allows us to use familiar terms that we've already computed, like the voltage gain, and we can simply find Vn over V sig by doing a voltage divider. So we see that what we end up with is V naught over Vn multiplied by Vn over V sig. So we know that this is just our voltage gain, AV, and we see that in our new circuit, the only voltages is Vn and V sig. So whenever we see that and they're in series, we instantly know that we can just do a voltage divider. So what do we have here when we do voltage divider? We have Vn equals Rg multiplied by V sig over R sig plus Rg. So now when we just divide both sides by V sig, we're simply ending up with Vn over V sig equals Rg over R sig plus Rg. So now we have our two familiar equations in our overall voltage gain. We already know the voltage gain AV, and now we found Vn over V sig. So we simply just plug this in, and we get GV equals AV multiplied by Rg divided by R sig plus Rg. So that's going to be our overall voltage gain. And now finally the output resistance. So in the output resistance, as you might have seen in the transistor videos, we want to look at the place where the output terminal is. So what's interestingly enough is the original circuit actually looks like this. RD in parallel with RL, where only RL actually has the voltage output terminal, except they both do share the same voltage, but it does not mean the terminal is connected to both of them. Important to know. So as always, when we're finding a Thevenin equivalent resistance, we simply remove where the output terminal is. We can replace it with a 1 volt source or a 1 amp source, which has a voltage Vt, and we can simply write R out equals Vt over the current, which is 1. So we have R out equals Vt. Now, really important to note, now that we added a DC source, we have to deactivate the AC source. So what we're left with is this R sig. And we can easily notice that R sig is now going to be in parallel with Rg. So we can just simply erase everything in here and write it as one resistance, R sig, in parallel with Rg. Now you might ask, why do we remove the Vn? Because now that we don't have the voltage source, we see that the gate voltage is just equal to 0 because it's grounded and there's no current in it. So there really is no gate voltage now. So we can simply just write VGS equals VG minus VS equals negative VS. Now, just like the voltage gain, all we're going to do is we're going to do a KCL across this node right here and a KCL at this node. We'll actually label this in green just to make it pop out more a little bit. So once we perform our KCLs, we see all the currents are going down. We can simply write this as 1 equals, now we know VT is going to be the voltage across the entire node. So VT over RD plus VT minus VS over R naught plus GM negative VS. It would be GM VGS, but remember, VGS is equal to negative VS. So let's rewrite this as VT over RD plus VT over R out minus VS over R out minus GM VGS equals 1. Or sorry, minus GM VS. And now let's start with our second KCL. So it's just going to be the same as the one we found in the voltage gain because we didn't really change anything in this part of the circuit. So we'll have negative GM VS plus VT minus VS over R out equals VS over RS. So what we can see from this circuit is that we can easily just get everything in terms of VT by making VS a function of VT. So let's do that here. Once we move everything to its appropriate side, we leave VS on one side and VT on one side. We see VS, once we factor that out by VS, 1 over RS plus 1 over R out plus GM equals VT over R out. So what we can do here, we can divide both sides by whatever's in this bracket. We get a function for VS. VS equals blah, 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 blah. And then we can just plug this back into this KCL. And then everything will be in terms of VT except the 1. So what we can do from there is simply just do some algebra and we can easily find our R out answer by finding what VT equals to. So your final formula in this equation should be VT equals blah, 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 blah. Thank you guys so much for watching. I hope you enjoyed this. If you guys do want an algebraic tutorial on how to exactly solve this, then I can do that for you guys. But I hope you all learned something. Thank you guys for watching.